All right, so to finish this section off, I actually just want to double back to this cute little example of zeros followed by ones to say that we actually could do a little bit better than those two previous attempts. So the first attempt we had here was running in like big O of n squared, the idea of grab a zero, grab a one, grab a zero, grab a one, grab a zero, grab a one, rinse and repeat over and over and over. Then we step back and we're like, okay, we could totally do better than that if we cross off half of the zeros, cross off half of the ones, rinse, repeat, rinse, repeat, rinse, repeat. So we had an improvement. We went from big O of n squared down to big O of n log n. What I'm going to say is that we can actually do just a little bit better if we allow this machine to cheat just a little bit. So what happens is that in the world of Turing machine, there's a variety of modifications you can begin making. One of the modifications you could do is you could actually introduce a second tape. So what would happen is we'd have this initial tape that would be filled with all of these zeros and ones, and then I could have another tape that maybe runs right on alongside of it. What's going to emerge is that both of these tapes actually have their own little control unit. So there's going to be control unit A and control unit B. If you allowed for 3 tapes, you'd have A, B, and C, and so on and so forth. So if I allow for having multiple tapes, we can actually speed up this process from big O of n log n down to big O of just n, which is equivalent to just reading across this tape one time. So the way that we can do this is actually really cute. So like I said, it's worth just mentioning this kind of cheating aspect just because it's kind of fun, and it'll at least give us a few talking points at the end of this section. All right, so I think that's enough blank spaces. I'm not entirely sure. So one way that we can actually accept this input of 7 zeros and 7 ones is the following. So like I said, both of them have their own little control unit. So what I'm gonna do is I'm gonna read across that top one. And as I read across, I'm basically going to X out the zeros, and I'm gonna begin pasting a 0 into the second tape, which is totally fine. That's not a 0. I'm about to make another X. So go and go and go. So what happened here is that that little control unit then is now sitting way over here. So I'm about to read a 1. So what that's going to tell me is that my other little control unit's now going to start going the opposite direction. So as I cross off these ones, I'm now going to cross off the zeros. So effectively, that second tape is functioning almost just like a counter. So it went up, so it incremented every time it found a 0, and now it's going to decrement every time that it finds a 1. So if I have a match between the zeros and the ones, well, then my second tape is going to end back at the beginning, and that I would have X'd out everything that I should have because there was a perfect balance between them. If you had something that was like 0, 0, 1, 1, 1, well, what's going to happen is that your first tape would then end up with X's there, and your second one would have 2 zeros. And then as you X'd these things out, those ones would get X'd out. And then you'd be still staring at that last one, and you'd have nowhere for it to go. So it actually springboard this notion of rejection between them. So it's a really dumb kind of hack on it that you can go across this tape one time. So 14 total reads, and you can actually accept this little string that has zeros followed by ones. So this was adding in the cheating aspect of having a second tape, which initially maybe sounds like it can do tremendous things, except for anything that can be solved on a single tape machine, or anything that can be solved on a multi-tape machine can actually be solved on a single tape machine. It does not add anything to it, but it does possibly improve the speed of it just a little bit. So within the world of Turing machines, there's any number of modifications that you can make to these things, just like we had modifications to the world of finite automatons. If you remember, we had initially deterministic ones, and then we began to introduce non-deterministic ones. Same type of thing can actually happen in Turing machines. All of the Turing machines that we have been building up have all been completely deterministic, is that we knew exactly how we marched through this thing. There was no crazy like web of possibilities that emerged. There are versions of Turing machines that allow for that kind of possibility approach to occur, and they are referred to as non-deterministic Turing machines. So there is a huge debate in the world of computer science about what can you do on a deterministic machine compared to what you can do on a non-deterministic machine. And you've probably seen the little debate before. If not, these are two new little symbols for you, is this question of P versus NP. So the P notion is going to be something that can run in polynomial time. So things like n squared or n cubed or things like that, which all of our machines up till now have been able to do. The NP is going to be also polynomial time, but it's going to be done on a non-deterministic machine. So if you've ever dabbled into the multi-million-dollar question that is P versus NP, the official thing that's living behind the shadows is things that can be done on a deterministic Turing machine versus what can be done on a non-deterministic Turing machine. So there's debate about whether or not they can actually do the same stuff. So the idea is that, does non-determinicity actually give you anything new? So in our finite automaton world, that didn't give us anything new. So we had deterministic, we had non-deterministic, they ended up being the exact same thing. The debate is still open for Turing machines, is whether or not a deterministic one can do the same thing as a non-deterministic one. So there's people that vouch for either side of that argument, either the yay side or the nay side. But I figured it was worth at least mentioning now because you've probably seen something that says P versus NP. Well, the N means non-deterministic, the P means polynomial, and we're talking about Turing machines, so hooray. Anyway, in our next topic, we're actually going to be leaving the world of these cute little machines behind. As I alluded to, I like chatting about them as kind of warming us up for discussions of complexity, of being like, okay, how challenging is this process to go through? Do I need to have multiple terrible nested loops in order to do this, or could I possibly improve this a little bit? Or how bad do things actually get? So the next little bit, we're going to be chatting about this world of algorithms and trying to actually implement them and seeing what they're actually capable of. And then at the end of the course, we're actually going to jump into the world of information theory, which is then going to have some aspects of cryptography and all of the goodies that emerge there. So we're really going to try to only deal with terrible questions and that are really, really hard to solve, because that's where they're going to kind of get their additional security from. So we'll chat about algorithms, implement them, design them, do all of the amazing things that we know and love with them, and then end things up with a nice little discussion on cryptography. So hooray, lots more to come. Enjoy, have fun.